Okay, so we are starting today with the reciprocal lattice, and after that, in the previous lecture, we were introduced to the idea of a lattice vector. Sorry about it. I'm going beyond. Okay. The fact that the reciprocal lattice is a lattice forces us to write down its vector in the same way, meaning we have three primitive vectors, b1, b2, and b3, and we have the indexes, the numbers, integers that multiply them. Okay, so what's the relation between R and K? The relation is we would like any function of the form exponential of I K dot R to be equal to this is the requirement, this is the way that we fulfill this requirement. Okay, why does it make any sense? Okay, let's think about a wave in this lattice. Why do I have waves in this lattice? Well, for the next couple of the next lecture, we'll talk about electromagnetic waves in this lattice, to be more precise, Röntgen waves, very short wavelengths radiation. But it is also will be true and very useful if we are thinking about electrons in these structures. For the simple reason they are also waves. So, what does this condition basically tell me? That if I have a lattice, say some lattice, going to a simple two-dimensional square lattice. If I know the value of the wave here, in a steady state, has to be equal to the one here. Why? Because there's nothing different between this point and this point. It's translationally invariant. There's even a deeper point here. What have we learned last year, I guess, from the conditions that space is translationally invariant?
Nothers theorems?
Hmm?
Nothers theorems? Oh, too far.
You're going much too far ahead. What did we learn out of the conditions that there's no difference between different times in the universe? Translational in time.
Conservation of energy.
Exactly, conservation of energy. The fact that space is invariant to translation, what did we learn from that?
Conservation of momentum.
Conservation of momentum. A lattice is a very strange situation because on one hand we don't have any more translation and invariance. Right? This point is not equal to this point. But we have some remnant of translation and invariance. Meaning that if we jump to a different point that is different by the lattice vector, then I still have invariance. So to the more mathematically inclined, we changed a continuum translation invariance that we have in empty space to a discrete one in the lattice. Okay, so all this is motivation if you don't really dig into what I really mean, no problem. In the meanwhile, this is just the definition. I want a reciprocal lattice that is built out of vectors k that fulfill this condition. What will fulfill this condition? What should appear here in order that this condition will be fulfilled?
2 pi n.
2 pi n. Where n is any integer. If this is fulfilled, great. So the condition is fulfilled. Okay, so now my problem is just how do I get B1, B2, and B3 out of A1, A2, and A3? Okay, to do that, we'll just use something that we learned about properties of vectors. Okay, why does that help us in life? Because okay, and then it's simple. Anytime we will try to multiply, if you don't see it, either refresh a bit the knowledge about vectors, or you can try it by yourself and convince yourself that this is true. Why is that true? Delta, you're familiar with the Kroneker's delta? Well, we did quantum mechanics, you have to be familiar with it. So why is that true? Let's look. If I multiply it by A1, then I have, according to this, 1 times 2 pi. Okay. If I multiply it by A2, cross is always perpendicular to either A2 or A3, therefore it's a delta. So if I construct B1, B2, B3 in the following manner, I assure that this will be fulfilled. Or if you want to see it explicitly, Okay, because of this condition. And since all these are integers, so we have an integer multiplied by 2 pi. So which was the requirement for the reciprocal lattice. That's important for something. What is a reciprocal of a reciprocal?
The original.
The original one. Clearly, because I have to fulfill this condition, I have K, so it must be R. So it's R. Okay, let's do a few examples. Okay, I forgot last lecture someone asked, what are we doing out of Ashcroft? So previous lecture was chapter 3. Sorry, chapter 4, and the current one is chapter 5, and hopefully towards the middle of the lecture we'll move to chapter 6. Not immediately.
זה הלוח, הוא דפוק.
Maybe you want to try tissue?
Well, I guess this guy went to bring from the secretary. So, do I have another volunteer? We'll try. לראות עם חדש כזה אולי.
לא, זה הלוח והסושי ביחד.
לוח בעייתי, מה נעשה אותו?
ספרי?
מקדמה. הלוח זה לא...
מה שמפריע בשיעור האחרון זה היה פחות גבוה.
או שעובר יותר זמן.
כל פעם המנקה באה, ולא יודע מה היא שמה על הלוח, אבל זה...
So we'll have to try to survive with what we have.
מקסימום כשאתה מרגיש שזה עמוס מדי, קח איזו הפסקה של 5 דקות, נעביר על זה ויש ו...
May I ask questions, please?
Yes.
Why do we have to use R only? I mean, R really is suitable for this for the terms over there. But what if I chose 2 times R or 3 times R or something else that could hypothetically solve
But
this?
there's no point in choosing 2 times R, but unfortunately I've wiped it already. R is any vector that is built out of the primitive vector, so it includes twice, 4 times, billion times, whatever.
And other combinations that could also solve this.
R is not a specific, it's any
Yeah.
vector that is built
How do we
out.
know that there are no more options other than R for this?
Well, it comes out from the same theories that you used in quantum mechanics to build bases. Completeness and all that stands behind it. Because at the end of the day, this is just Fourier transform. Nothing more, nothing less. And if you want, what's it called, this? You have a chapter, or at least a few paragraphs in a chapter of, not, what is the second book? Not Boaz, basic method.
Label? No.
No, not Lego. I'll look at it when I get back to my room, and if it's important, send me an email. But just orthogonal bases. That's all you need to know, because these are orthogonality type of conditions. Okay, so let's be less abstract and see a couple of examples. Simple cubic is very nice because it's very simple. Okay, since these are perpendicular to one another, will give us ax dot a to the third.
בריבוע. למעלה.
Right. Life's good when you have simple cubic. Exactly the same way.
B1. A1 is okay, but about B2, it's supposed to be A1 cross A3, and then the bottom part is supposed to be A2 dot.
No, it doesn't matter because they are the same. The only thing that perhaps I've exchanged 3 and 1. All that it will do is will put you on minus, but it doesn't really matter because then you just get the same indexes but with a minus. So okay, let's look at something more interesting.
אני בכל של שורות האחרונות בבקשה, את השתיים האחרונות. להשלים רק את ה-B1 בבקשה.
Okay, so let's look on the case of FCC. Just don't want to erase this part because I'm using it. So, okay, so for those of you who forgot how we do a cross product, Y, Z, okay, so I wrote the determinant of the cross product. Do I have to remind you how to perform it? Okay. Can I wipe this thing?
Not minus.
Let's check
The
for
accent, I think it's minus.
could be, let's say this guy
X covered minus.
minus
Y is okay, and Z
y is okay, and z,
and Z
that is also okay. So I just copied my result, and if I multiply it by A1, I get here A square over 8 times 1 plus 1. just this multiplied by this,
Isn't it supposed to be a to the third?
a to the third, of course. Okay. Would return with the calculation for B2 and B3. The results are and if you'll go back to the previous lecture, which lattice is this? BCC. And if I will request to what is the reciprocal lattice of BCC?
FCC.
FCC, of course. In general, I won't prove it, but I'll state it. Well, here is the volume.
Volume in the lattice means the volume of the cell on the lattice.
Yep. Volume. Didn't want to write the whole primitive. On the full exact definition. Okay, another definition. The Wigner-Seitz cell is, we have learned in the previous lecture, that this is a primitive cell that we built by drawing the perpendicular planes to the vectors A1, A2, A3. In the reciprocal, it sounds just giving names, but this term, the first Brillouin zone, will be very, very useful when we do quantum mechanics of electrons in lattice. So that's just the definition. Okay, so we have our mathematical background. Now we'll start to consider some physics. Someone wants to guess what this is?
Quartz.
Quartz. Silicon O2. Yesterday I brought you very small pieces of it. This is a large, nice specimen. And what's the first thing we notice about it?
Reflective.
It's reflective, but look on, it has planes. Anyone who looked at any gemstone knows that what gives it its beauty is the planes of the stone, of the lattice. Why is it? Basically because these, any lattice is easier to cleave. Now I can remove it. And I'm drawing it in 2 dimensions. If I try to break a piece of this lattice, breaks easily along planes. This is an example of a plane, but it could be also this plane, an infinite number of planes. And basically, the first clues that we have in ordered structure came from thousands of years ago when people understood that crystals can be broken cleanly along these geometrical planes. So even before we go into complicated techniques like X-ray, just the fact that when you cleave a piece of crystal and it gives you these nice smooth planes is a clue that it's basically built like a lattice. So here is another lattice. This is calcite. It's calcium and oxygen, basically. Another example where you see the structure of the lattice. It's heavy, so this at least is heavy. Just put it on a paper and see what you get. Put it on your tablet, you see something interesting. See double. That's because of the structure that's birefringent. Light has two paths that go through in different, where the light has a different speed of propagation, and that's why you get this birefringent. I don't think we'll get to it in this course, but it's an interesting effect of lattices. And as you can see, these specimens are quite old and they start to show cracking in them. Okay, so we need a language. We want to say along with which plane did we cleave the lattice. How do we do it? Okay, so the accepted way is write a vector which is perpendicular to the plane. Now, what are these vectors? Let's define the distance between the planes d, because I have an infinite number of these planes. And I claim that is a reciprocal lattice vector.
Does this also work for lattices that have more than one particle in the cell?
This is for a Brevet lattice, where I have a point. Usually what will happen is you have more than one point, you're breaking along one of those atoms the same at every point. That's how you define your Bravais lattice. Okay, so why is this true? What do I need to prove in order to say that this guy is a reciprocal? I have to prove this guy. Or I have to show the p to the pi. Okay. So, what is R? R is lattice. Okay, so I can decide to put my my axis to begin. Okay, I'm using a different color. Right, R will be anywhere on this plane, and for this plane, it clearly comes out 0, right? That would be true for any plane. So K dot R here,
K dot M.
K dot N, 0.
1.
The easiest proof you ever have seen. Okay, so N up to a normalization, a length, is basically use the usual notation. So I wrote down the reciprocal lattice vector. Just instead of M1, M2, and 3, I use N, K, and L. Why? Because that's a notation. And if I want to write down to what plane I'm referring, I just write down N, K, and L of the reciprocal vector, which is representing the perpendicular vector to the plane. So in 2 dimensions, let's see this guy, and that's called the Miller index. So these planes will be in 2-dimensional. I have only 2. Will be plane 1, 1. This plane, let's take a different color for it. What will it be? 1, 0 or 0, 1, depending on, I think usually it's 0. So on, 2, 1, 7, 1, whatever you want. In a simple cubic, what will be plane 1, 0, 0? Just have here. Let's assume that this is a cube. It's not, but okay. So 1, 0, 0 would be this plane. 0, 1, 0 would be this plane. 0, 0, 1 this plane. If I take something that goes diagonally, it will be 1, 1, 1, and an infinite number of such planes exists. Okay, who cares? One cares because in the beginning of the 20th century, a new toy came into the game, and that's X-rays. Or at the time it was mainly called Röntgen rays. And when you point X-rays at a lattice, you see that you get reflection of these rays only in certain directions. And basically, two physicists, Bragg and von Laue in England and in the UK, came up with the explanation what happens. Okay, let's see first Bragg's formulation of the condition for getting reflection. And Bragg used based his explanation very much on these planes. Okay, let's assume that we have two planes. So let's say I'm shining an electromagnetic wave, in this case an X-ray, on these planes. Some of it is reflected from the first plane. Some of it is reflected from the second plane. Okay, let's define this angle as theta. So the part of the wave that was reflected from the second part, from the second plane, had an additional path of these, the length of these lines. That's calculated. Okay, if this is theta, this is theta. So I hope all of you see that this is also theta. 90 minus theta, theta. So if this is our beloved d, the distance between the planes, so this is d sinus theta. So the additional length that we have in the second pass is 2d sinus theta. Now, if this length doesn't correspond to an integer times the wavelength, we'll have destructive interference from all the layers. Because I have here an infinite number of layers, or at least a very big number of layers. So I'll see reflection only if this condition is fulfilled. Okay, so I have a bunch of thetas where this is fulfilled. All other angles will see no reflection, because the destructive interference will kill the wave. Now you can come and say, just a moment, these planes are something I'm drawing in my imagination. I really have points here, not planes. This is taking intuition out of simple ray optics and using it here. Did we miss something by that? The answer is no. And that's von Laue showed in the following argument. Okay. So von Laue said, let's look on 2 points in the lattice. Let's assume that the distance between them is a vector d. Now I have an incoming plane wave. And actually I'll draw it perpendicular, although it's not very important. Just it would be easier to see, it doesn't change anything. Okay, so I have a wave that is coming in direction k. I'm giving this curl to the k that we won't get confused with the k of the reciprocal lattice. And that comes in some direction let's call it 2 pi lambda over n. Okay. Let's assume that it's scattered. And when it's scattered, of course, it comes out in all directions. But I want to know what happens in a certain direction, k prime.
Excuse me?
Just a moment. Which is in the direction n prime.
What is L?
This?
No, on the bottom, the left line.
D.
D.
I D. What is it?
Just a vector between the 2 points.
What are the 2 points is?
2 lattice points. I chose them at random. Okay, so I have an incoming wave in direction n, an outgoing wave at direction n prime, and because those are optical waves, so it's k is 2 pi over lambda. Okay. Again, what is the additional distance that this wave has taken more than this wave? These 2 paths.
The spacing between the rays is the same as the spacing between the crystals?
Well, I can move the crystal and the spacing will... The only... What will happen, basically? Okay, that's something perhaps...
No, but also your diagram there, the spacing is the same, otherwise you can't, it's not the same angle. What I don't quite get it as the... Are we sending in X-rays at the same distance?
You're sending a plane wave.
Yes.
Okay? I don't want to clutter this... Okay, let's do another drawing. That's the wavefront of what I'm sending, okay? Let's put in here a couple of points. Okay, for here it would be easier to see this guy, okay? Okay. Progress, progress, progress. Hits an atom. What happens here? Did you ever spend any time close to a pond?
Oh, refraction?
You'll get an outgoing scattered wave with circular properties, right? Next time that...
Yeah, to lose its resonance.
Most of it just goes through, and the part that is scattered comes out like spherical waves. As long as the scattering object is small, at least to first approximations, this is exactly what happens. Any time that you're in a pond, either throw a stone into the pond and see that you'll see circles coming out, or if you can find a nice beach where you have just one rock somewhere and look what happens around the rock when the waves come out, circular waves. Okay, so, and the same is here. Okay? But now we're sitting a long distance from here. We're trying to see what happens when I'm looking on the page from here. I'm a long distance from here. I don't see the scattering of each spherical wave. I get a wave coming back to me. So these will combine into a wave that goes in this direction, and I'm trying to measure, that's known as far field. I'm trying to measure the field far away from the point of scattering. So I'm assuming I have an incoming plane wave and an outgoing plane wave. So these are just these arrows. Most of, it's very important, most of the ingoing wave will hit nothing and just continue on. This is a small percentage of the incoming wave that is scattered in some direction. But I want to ask, is it small or zero? And this is the point of this calculation. If the angle doesn't fit this condition, it's zero. If it fits, it's small compared to the intensity you send in, but still can be measured. In any X-ray experiment, in any optics experiment where the scattering at the end of the day is small, you have to put here a large bulk of lead. Otherwise, your friend sitting in the next room will be irradiated by a lot of X-rays. Not recommended. Okay, so again, it's the same picture, but now I'm looking at points, not on planes, which you can say is more natural, makes more sense. Well, it's minus because n prime here is in the opposite direction. And d, well, here it's in the same direction. Okay, and the same as in Bragg's description. And coming out from the geometry. That's the phase that you gain going through this path. 2 pi over lambda times the geometry. This has to be an integer multiplication of 2 pi. Okay, what is D? If I take any 2 points in the lattice, what is D?
One of the hours.
It's R. Some are one of the R's that constructed this lattice. The reciprocal lattice vector, right? Because this guarantees that if I multiply R by K, it will be 2 pi times n. So basically, what does it tell you? You want to know in which directions you'll get scattering, where the interference won't kill you. The incoming K subtracted from the outgoing K will be equal to a reciprocal lattice vector. Of course, you have infinite such directions, but it's a discrete set of them. Not in any direction that you look, you'll see X-ray coming out. Now we'll see when we'll consider. This is actually a very deep result. Because what does it tell us? If I had nothing there, meaning no lattice, nothing, homogeneous piece of material, will I have scattering? No. In that case, the reciprocal vector is 0. And K is equal to K prime. Conservation of momentum. You don't scatter it, it continues in the same direction. The fact that you have here a lattice scatterers arranged in a certain structure forces you to be, allows you at least to be scattered, but not in any direction that you want. Only in a discrete set of directions, which are the reciprocal lattice vector. Yeah?
In a homogeneous material, it's either you'll get a transmission through the material, or it will just bounce back, right?
No. Where you get a transmission and reflection?
For instance, mirrors.
What signifies a mirror? Let's look on this piece of glass. You had one medium, a different medium. This is not homogeneous.
Oh.
It's very important. as long as you're completely homogeneous, you have no scattering. Once you enter the glass, you don't scatter until you meet the other end.
Okay, thank you for the clarification.
Yeah.
But it is n minus n prime not plus. Yeah.
Here, because n is in this, n prime is in this direction, okay? And d is in this direction. So if I multiply d dot n will give me a minus. On the other hand, here it's n and d are in the same direction. So if I'm calculating the distance, I have to put in the minus. Okay. Now, this relation has a nice, or perhaps it will sound at the moment presumptuous name, but we'll use it once we get to electrons. This is basically called quasi-momentum conservation. If we had no lattice, momentum conservation will tell us that k is equal k prime. Here it tells us that k prime is k minus some reciprocal lattice vector. It sounds at the moment somewhat mysterious. We'll meet it in a month or so. Okay, the last, well, almost the last thing that I want to do. Okay, this, how does it connect between themselves? I said in the beginning that there are two formulations that are the same. What is this condition? Someone can guess what does this condition mean?
Magnitude of the momentum?
Yes, this is what's the physics behind it? Yk will be the amplitude of k will be the same as k prime.
Energy conservation.
And exactly, energy conservation. Means that we are not transferring any energy to the lattice. An assumption that works very well. So I know that the magnitude of vector k is equal to the magnitude of vector k prime. Or lambda is equal to lambda prime, which is actually what we have written to begin with. So if I rewrite what appears here, Okay, I just transferred. Taking the absolute value of the vectors. But this is equal k, so I can write So what is a reciprocal lattice K? Reciprocal lattice perpendicular to some plane. That's how we started the lecture. Or look drawing. So we have here the reciprocal lattice K. We end up k dot k prime is 90 minus theta. So is and we end up with so basically the two conditions are the same to my taste, and also in general use this is the most concise and clear definition of in what direction will we get an X-ray reflection. Okay, in the next lecture, we'll say a few words on how it's measured. And then continue to ask the question that was asked here in the beginning. Wait a minute, what happens if we have more than one atom in this lattice point? And additional questions like, what happens if the atom has a finite cross-section, it's not a point? All these will change the results a bit, but basically this will remain the main result on where are we getting the reflection from the lattice. Okay, just please return the